Hi everyone. Today we're going to do a lab where you use two techniques to measure the speed of sound. Now, you might think, modern physics, why are we talking about sound waves? Well, the important thing for us is that sound waves are an example of waves. We're going to spend a lot of time talking about waves because we'll find out that everything, all types of matter, all types of energy can be described in terms of waves. So it's important to brush up on our wave mechanics. So first, what is a wave? Well, think about that for a little bit. Waves are different than particles. For our purposes, a wave is a disturbance that travels through space at some velocity. Okay? It's a very general definition. But even from that definition, a lot of interesting things follow. Here, I'm going to show you a demonstration. 1 second. Okay, to get a wave that travels through space at a fixed velocity without changing shape, the wave has to depend on time and position in a particular way. Okay? So the wave can be any function, f of u, so long as u is either x minus vt or x plus vt. This is for a wave traveling in the x direction, of course. So let's look at an example. Suppose that my function, f of u, is a Gaussian function, e to the minus u squared. If I run this, you can see that that dependence, u equals x minus vt, gives us a wave that travels through space at velocity v. Okay? And if you think about it, that's just what you expect. If at t equals 0, our function peaks at in a certain position, then as t gets larger and larger, the peak will occur later and later, or further and further from the origin. If we change our function to x plus vt, things will change in a kind of obvious way. Can you guess what will happen? That's right. Now we'll get a wave that moves to negative x instead of positive x. As I said, the wave can have any shape we like. Here it had a Gaussian function, but it could have a sinusoidal function, like so. Here, let's change this back. There we are. Now we see our well-known wave shape that has a well-defined amplitude and wavelength and frequency. Okay, sinusoidal wave. But it doesn't have to be one of these types. It could be anything we like. Here's one. Here, this looks like a sinusoidal wave that's modulated by a Gaussian function. This shape sometimes we call a wave packet because it has a fairly well-defined wavelength, but it's also fairly well localized in space. More about wave packets later. Okay, so that's just the first thing about waves. Okay, the second thing we want to talk about with regard to waves is what happens when you add two of them together. For a wave described by a linear differential equation, in other words, for linear waves, when you add together two waves, like the red wave here and the blue wave here, you just get the simple sum of those two waves. For example, here I have two waves of the same amplitude and same wavelength moving in the same direction, and when we add them, we get this gold wave, which is just, of course, the sum of them. It's twice as large. Suppose we added them, but with opposite amplitude. Then, of course, they'd cancel out everywhere. We'd have perfect destructive interference everywhere. Okay? By the way, constructive interference, destructive interference, this is something that waves exhibit that particles don't, at least in our classical conception. Okay? Now, for us, something that's really interesting is what happens if the waves are moving in opposite directions instead of the same direction. So now we'll make one of the waves move to the left. There we go. Now we get something really interesting. Let's sit and watch this for a second. Okay, now look at the gold wave. can you see that for the gold wave, at certain positions, like the position of the cursor right now, the amplitude is always 0. Here's another one of these points. These are called nodes. And then, as you might remember, the points in between the nodes, where the oscillation amplitude is maximal, those are called antinodes. This whole pattern, which oscillates in time, but doesn't move through space like the red and blue waves do, this is called a standing wave. And what you can see immediately is that the standing wave was created by adding 2 waves with equal amplitudes and opposite directions. Equal amplitudes and frequencies and opposite directions. Okay? We've already explored the case when they're both moving in the same direction, no standing wave there. And we can imagine what happens also if they oscillate with amplitudes that are not quite equal. Like so. Then we get something that looks a little bit like a standing wave, but not quite. It's more complicated. So what I want you to keep in mind is that one can have standing waves, as we've just shown, or one can have traveling waves, like the red and blue waves. Each of these are traveling waves that move through space. And standing waves are actually just composed of traveling waves. All right, that's our basic qualitative introduction to waves, okay? And we'll look at the properties of traveling sound waves and standing sound waves in today's lab.